recording on the computer. Hello, everybody at home. We're done here taking the quiz. So we're going to go ahead and start up and finish chapter 10. So chapter 10 was all about radicals, okay? Radicals only do two things. What are they? Abstracting a hydrogen to create a radical, or adds to a double bond, creating a radical on the second carbon. Those are the only two things it does. Okay, and then there's a radical annihilation, but that's one of those steps. There are three steps in every radical reaction. Initiation, usually brought on by a peroxide, but we have some other things we can do, or light or heat. And then there's propagation, where every time one of those radicals is generated, it generates another radical. And so then it can continue and continue and continue until, of course, all the stuff's done, or we get to those termination steps where radical-radical coupling can be productive, like forming bromine, two bromine radicals, or it can be your product of methyl radical and a chloride radical, or it can be two methyl radicals, which would be non-productive. So we have only two things that can happen and three steps in every mechanism, okay? And then we found out that the shape of our radical is analogous to that of the carbocation. And therefore, the stabilities of radicals were analogous to carbocations, including things that are conjugated. We have the allyl radical here and the benzyl radical here. They are also conjugated, and therefore that makes them even more stable than tertiary radicals, just like our carbocations. So what we ended up with is the resonance stabilization gives those radicals more stability than our tertiary. So we're actually going to use them, and we're going to create allylic halogenation and benzylic halogenation that works well. More stable means forms faster. If it forms faster, you're going to have more product. More stable means lower activation energy. Lower activation energy means more product, okay? And then because of the high rates of formation for those benzylic and allylic radicals and cations, these can be problematic because now you might have choices. Now, in this lower thing here, we have our resonance structure for what we have, and we have our allylic radical here, or we can take its electron one barb, and one of these electrons, one barb, and then put the other one here. And that gives us this. What's the difference between those two allylic radicals? This is a secondary and this is a tertiary. Right, so it's going to spend a little more time on the tertiary side, even though they're in resonance, which means your tertiary product is going to be your major product. Okay, now in this second example here, what we have is we have an allylic radical, and when it comes in, one electron here and one electron here to get your double bond, and then one electron up here, we end up with another radical here. Here we have a secondary radical, and here we have a primary radical. Where is it going to spend more of its time? In the secondary position. So your major product is going to be the secondary. Your minor product is going to be your primary. Okay. Now, is there any way to, sway it one way or another? Not really. The only way you can do it is sterics, but still the tertiary is much more stable, and it's going to be formed faster, and therefore it can react faster. Okay. Questions on that? Okay. Well, the cool thing about this is it gives us an opportunity to do selective reactions, regioselective reactions. And one of those regioselective reactions we have is the halogenation of the benzylic site or allylic site with that just having bromine there. Okay. Now, what's the problem with just having bromine in your system and having an allylic or a benzylic cation? Well, your bromine can add across the double bonds, right? It can brominate that double bond, and then you can have a secondary bromination. So, or it can add across the double bond using a different mechanism, right? It's cold in the dark, it adds across the double bond. So you have two possible reactions competing with each other. Okay, so what we're going to do is we're going to so we have very little bromine available at any one time. And therefore, it's going to act as the radical and not as the bromine itself. Okay, so how do we do that? Well, we're going to replace bromine with a compound called N-bromosuccinimide, or NBS. There's also the iodine derivative is also available, but we're going to do NBS, N-bromosuccinimide. What that means is the bromine is on the nitrogen. That's why that N's in the front there. Okay, so that's a weak nitrogen-bromine bond. And we can break it in the presence of heat or light or just peroxides to generate. Notice that it's going allylic. We are getting that allylic bromination. We are not losing our double bond. We're not getting dibromination from the bromine. Okay, and then it ends up transferring the hydrogen that was here, gets abstracted and gets put on the succinimide itself. Okay, so what this means is when we're doing it, we have a very low concentration of bromide radical. So the bromide radical will be able to eliminate those undesirable side products. And it also works on benzylic cations, where you don't want to halogenate some other portion of your but it's most important in allylic, because what you're going to end up with is a bromine next to your double bond. You're not going to destroy your double bond. Okay, so how does it work? Well, it works by keeping the concentration of bromine radical very low and keeping the concentration of bromine element, diatomic bromine as well. So let's do what we do in every radical reactions. We do an initiation step. So in our initiation step, we have peroxide breaking up to form our two radicals on oxygen here. Then we can use, or we can actually have this weak bond between the nitrogen and the bromine break off to generate a little bit of bromide radical and a little bit of the succinimide radical. Okay, so now we go to our propagation step. So we can only add across a double bond, which we don't want to do, or we can abstract a hydrogen. So that's what we're going to do. We're going to abstract a hydrogen, and we're going to extract the hydrogen next to the double bond. Why? Because it's going to make the allylic radical, which is more stable. So it's not going to add to the double bond. That's going to be less stable than it taking the allylic hydrogen away and giving us that radical there. So now that we have our radical here, and we have the possibility of generating HBr or an alcohol from that product, we can, and so we can actually have the alcohol radical abstracted or the bromine radical abstracted. But we just made the bromine radical here, so we're going to use it. Okay, so then the next thing that happens is the bromosuccinimide acts as a base. Acts as a base, right? Well, it has that lone pair, so it's a Lewis base. And it's going to deprotonate the HBr we just created and create this salt. And when we create this salt here, we can actually have this act as our nucleophile and break that weak bromine hydrogen bond, nitrogen bond again, giving us a little bit of bromine. Okay, once we get a little bit of bromine, that can react with our allyl radical to generate our product plus a bromine radical. And the whole thing starts over again. And then at the end, you're going to end up with all of the hydrogens being abstracted by the succinimide, and that's going to precipitate out. You're going to have all the bromine that isn't used converted into HBr, but anything that gets converted to HBr gets turned back into bromine and can be used again. So it just keeps going and going and going until you run out of reactions. Okay, so the whole thing starts with the idea that the hydrogen abstraction gives you the allylic radical. The allylic radical is going to give you your product. And you're saying, well, okay, but this is an allylic radical. We're going to put one electron. We can move one electron here, move this electron here, and put the radical here. In this substrate, it doesn't matter which side of it does. It's a secondary allylic radical on both sides, and the product is symmetrical. So we're lucky that we chose a product, we chose the cyclohexene, which will give us that 3-bromo cyclohexene, no matter which side of that allylic radical it attacks. Okay, questions on that? Okay, all right. So that means we have some regiochemistry associated with it. Okay, because we're going to be forming two different allyl radicals. Okay, in this case here, if the double bond is on the end of the chain, we're going to abstract this hydrogen here to give us our allyl radical. And then we can have that radical be on this carbon or this carbon, which means we should get product on the 1 carbon, and we should get product on the 3 carbon. Okay, and so if we generated the radical here, and we had the bromine or the bromine radical make the new sigma bond here, it'd give us the 3-1. Now, if we had the other resonance structure, the radical would be here, the double bond would be here in the middle, and that's where we get the 1-bromo-2-butene. We get the 1-bromo-2-butene because it was attacking the primary radical. Okay, so let's look at that. And so we have, again, our bromine radical we've generated in the system by taking just a little bit of that bromine and getting it to react. We're going to do hydrogen abstraction, and that gives us this radical and this radical. So if the bromine reacts with this one, we're going to get the 3-bromo. If the bromine reacts with this one over here, we're going to get the 1-bromo. Okay, and that's because of our hybrid resonant structure. We have half a radical on one and half a radical on the other, and therefore, we're looking at maybe it's going to spend a little more time on the 3 position because that's a secondary radical. So we might have a little bit more of that, but we're going to have definitely both of them are going to be products in our system. Okay. All right. So radicals are kind of cool. The mechanisms are fairly simple. They can only do 2 things. They have 3 steps in every mechanism. They're the same thing. All that changes is your substrate. Okay. And as long as you know the stability of them, you'll know which side of it's going to react first. Because whichever one's going to make the most stable one is going to react first because it's lowest in energy. Okay, so why do we care? It's problematic for some things. It can make products that maybe are 2 things. Well, where it's really used a lot is in industry. Okay, and in industry, especially making polymers. Okay, so or what some of you call plastics. Okay, so we're going to use radical chemistry to make plastics. Okay, so let me tell you what a polymer is. Poly means many, mer means units. So basically it means many units. Okay, so basically it's a long chain of repeating units that are all made up of smaller units, and those smaller units are called monomers, 1 mer, 1 unit. If you have 2 of them, it's a dimer, 3 of them, it's a trimer. But so you can see where in a reaction where you use a radical that makes a radical that uses the radical and makes the radical and uses the radical and makes the radical, this might be a great way to make really long chains. Okay, so when we do that, when the process of joining those monomers together, we call that polymerization. Okay, so basically it's just the propagation stage of our radical reaction. Just keeps going until you run out of things to react with. And then it terminates in our termination step, and we're done. Okay, so anything with a double bond in it and a group on it, Z. So Z can be a lot of different things. I'm going to show you several different examples. Z is going to tell you that these are vinyl monomers. So let's say the Z was a chlorine, that would be vinyl chloride, or it was a methyl group, that would be propylene. It'd just be something simple. The Z affects the physical properties of the resulting polymer. If Z is hydrogen, that would make that ethylene. Anybody ever heard of polyethylene? Okay, polyethylene, ethylene's a gas. You double that up, that's butene. Okay, butadiene, that's a liquid. You triple that up, and then it starts to become, after about 20 units, it becomes a wax, but it's really pliable. And then as you get more and more and more and more and more, it gets tougher and tougher and tougher until you have those plastic bags you have at the grocery store that we don't ever use. We use recyclable, reusable. Anyway, so that is polyethylene. They can also be made into tubs and other things. So it starts out as a gas, And as long as you start adding them together, they're going to change properties. Let's change it to C. So that's going to be vinyl chloride. And so that's going to be polyvinyl chloride, or PVC. PVC as made is that white pipe at the Home Depot. Really, really tough. And so you go from a gas to a really, really tough material. And all you've done is add a whole bunch of units together in a controlled fashion, okay? So let's look at that in a little bit more here. So we're going to take this monomer and add it to this monomer and add it to this monomer. And so what it ends up looking like is with this chain just keeps going and going and going, okay? And if we were to look at where those Z's are, they're going to be in the same place all the way along the chain. They're going to be always spaced 1 CH2 apart. So it's a regular structure. It forms one way in a regular structure. It must have something to do with the mechanism. So let's look at what's happening here. Okay, so we have our 3 steps in any radical mechanism. Initiation. So we're going to start it with a peroxide. We're going to break our peroxide bond, giving us 2 equivalents of that. And then our peroxide is going to attack one of the vinyl compounds. Okay. Which side is it going to attack? The side with the Z or the side without the Z? Without the Z, because as long as there's something here, that's going to turn this into a secondary radical. This is going to be a primary radical if it attacked the other side. So it's trying to make the most stable radical. So it's always going to attack on the end with the 2 hydrogens. Okay, and that means that we always generate our radical on the place with the Z. Well, now that Z is going to come in and it's going to attack exactly the same way on the side with the 2 hydrogens. And that's going to space the Z's out exactly 1 CH2 apart. And then that generates a radical. And it keeps going and going and going and going until we have so many units we can't count. That's what that bracket with the N means. It means we have more than 100, we can't count them all. So it's just some number N, but the repeat unit is the same, okay? And so then to terminate, we can either have the radical that we initiated way up here terminate, or we can actually have 2 chains terminate, okay? And it'll keep going until you run out of vinylene monomers. So you can start with something that weighs 120 molecular weight and end up something that weighs 5 million grams per mole. And their property will change up until a certain point, and then it kind of stabilizes out after a certain number. It's just, that's a tough polymer, and that's what it's going to be. Okay, so that's where it's really, really cool. But notice we didn't change any of the steps in the mechanism. And the same steps of the mechanism shows why we have regioregularity in our system. Okay, so let's look at the polyvinyl chloride. The polyvinyl chloride, the chloride, the radical is going to form next to the chloride right here because it has donation and it has high clouds here and all that kind of stuff. And so then it's going to attack this side of the other one. So we have, this is the, let me change to red. This is the new sigma bond formed. This is the new sigma bond formed. This is the new sigma bond formed. It's always from where that radical was over to the end of the next vinyl monomer, okay? But oh gosh, what happens if we use isoprene? Isoprene is a naturally occurring material that's found in rubber trees. And if you use radical polymerization, it zips up and turns into natural rubber. Now, natural rubber is actually kind of an off-white. The stuff we see on our cars actually has a lot of carbon and silica and a whole bunch of other things added to it, and some sulfur to make it cross-linked and make it really, really durable. But the polymerization is a little weird. Okay, so what we got here is we have our isoprene, and so something's going to initiate a radical on this side, right? So that means we're going to move one of these electrons here to form our bond here. One of these electrons is going to go there. Okay, what kind of radical is that? Is that just a tertiary radical? No, it's an allylic radical. It's an allylic radical because there's another double bond here. which means that radical is going to go back and forth between these two positions. Okay. This one has three things bonded to it. It's sterically hindered. This one doesn't. This is the one that's going to react with the next one over and the next one over. When it does that, it leaves the double bond. Only one of the double bonds is used in the polymerization. The other one just rearranges because it's an allylic radical. So when we look at this, this is our new double bond formed. This is our new sigma bond formed, new sigma bond formed, new sigma bond formed. And that other double bond was just participating as an allylic radical. But the radical itself is the thing that went off and did the next reaction. Okay. So now we have this really, really stable double bond, and it's kind of hindered, so it doesn't participate in the rest of the reaction. Okay. So the other thing we can do here is we can do styrene. Styrene makes durable plastic cups. You can make it really transparent. Sometimes it's opaque. It's also the stuff you make foam out of. Okay, it's a rigid polymer. And so it's styrofoam is actually styrene foam, polystyrene foam. So it's really good. Now, it has some benefits to it too, because now we have the possibility of creating a benzylic radical, right? So if we have something, our initiator come over here, and one electron forming a new sigma bond, that's generating a benzylic radical, even better than the allylic radical. And so it's going to attack the next unit in the exact same way. And we're going to have the benzene ring here. And then that's going to attack the same way in benzene ring here. Okay, so when we have too many units to count, we just put these brackets in the end, right? But the cool thing is they always react what we call head to tail. Okay, the leading more stable radical is always going to attack the least hindered side, and giving you the more stable radical, least hindered side, more stable radical, least hindered side. And it's a very regular pattern. Questions about that? All right. So that is how we do radical chemistry, but that's not the only way to make these vinyl polymers. Okay, because we have that resonance structure helping us. Okay, so in the case of other vinyl monomers, if we have an electron donating group that can stabilize a carbocation, we can use a Lewis acid to initiate the same chain type reaction. Okay, so what happens here is we have a Lewis acid that's going to interact and give us a cation right here, and something's going to attack it here and give us a cation. Now, if we have groups that have lone pairs, that'll help stabilize that cation, and it's going to be more stable than just a secondary cation. And then for that cation is now our Lewis acid. It's going to attack another vinyl group, generating another positive charge. And that's going to attack another vinyl group, leaving another positive charge. So this is a similar mechanism, except now we're using cations as our Lewis acids to attack our alkenes, which are our Lewis bases. Okay, so we have our nucleophile and our electrophile. So our cation is our nucleophile. No, that's not right. Our cation is their electrophile looking for electrons, and our alkene is the nucleophile. Okay, what if you don't have electron withdrawing groups that help stabilize that anion? What if you had electron withdrawing groups, okay, that can't stabilize that cation? Well, in the case of that, you can actually do antiotic, which means you attack something here with electrons, something with that is a Lewis base. Right here, it's going to use both electrons for here, kicking both electrons up here, giving you a negative charge. You just made a Lewis base, but you have to have electron withdrawing groups here, CN or nitro, to help stabilize that negative charge. So you're going to stabilize that negative charge by that electron withdrawing group, and then it's still going to act as a base, and it goes again and again and again. So these are almost the same reactions, but we're using cations and anions to do this chain extension, or this making unit after unit after unit. Okay, but they have some of the same similarities as one. Every time you make a new sigma bond, you generate a new reactive center. And then every time that makes a new sigma bond, it generates a new reactive center. So it can be a radical, an anion, or a cation. Okay, questions on that? Yes.
Is there a reason you would choose one over the other?
Yes, yes. For example, if you have something that's very electron rich, you could use the anionic. And there turns out there's, in some cases, you can actually have selective which way they go. If there's a chiral center, you can actually select which way they go. If you have something like acrylonitrile, it doesn't really like to do radical polymerization as much. And so it actually does these anionic polymerizations really well. They all do, but all of them do radical polymerizations. It's just that you can occasionally get different properties out because maybe you get different stereo centers. Okay, and that's the end of chapter 10. Okay, so we're going to take a break and take roll. All right, so what we're going to talk about in chapter 11 are alcohols and ethers, okay? And so first of all, I want to classify different ones we have. We have aromatic alcohols, we have allylic alcohols, and they kind of have different properties. So I want to classify them as alcohols that have an sp2 on them, sp2 hybridized carbon that they're bonded to, and those with sp3. Okay, so in the case of those, we have a good type where we have the alcohol right next to the alkene. And if you remember nomenclature from chapter 2, we call those enols. Okay, and so these compounds are enols right here. This is a one word, enol. It tells us we have that there. And when you go to chapter 12 next semester, you're going to find out why these aren't very stable. But I'm not going to tell you that. I'm going to let you guess. Okay, the other thing we have is one on a benzene ring, which is phenol. Okay, now remember, phenol is more acidic than regular alcohols because it has resonance structures. Okay, and so what's going to happen is we have a more acidic proton than we would have here or here. Okay, so we're going to use that acidity to our advantage. Now, if we space that alcohol out one CH2 unit from there, we have what's called an allylic alcohol. Okay, think about it. That OH is one carbon over from where the double bond is. So it's analogous to our allyl cation or allyl anion, but it doesn't move around like that. Now, if you have it one away from a triple bond, we call that the propargyl alcohol. And of course, using IUPAC nomenclature, the allylic alcohol is going to be prop2 ene 1-ol, because we're naming it for the alcohol. So the alcohol is one, that puts this as the 1 carbon, that's the 2 carbon, and that's the 3 carbon. So that's why we get our name 1, 2, and 3. That. And if we do that with the alkyne, again, the alcohol is naming it. So it'd be prop2 ene 1-ol. That's very hard to say quickly. And now if you have an alcohol in a benzylic position, it's called a benzylic alcohol. Okay, questions on that nomenclature? We're going to go back and review that again during our review, but there is nomenclature review on Canvas if you want to look it up today. Okay, so when we have ethers, we have something a little different. Number one, if we want to use a common name, we can say, well, if they're symmetrical, you have two of the same things, and you would like diethyl ether or dimethyl ether. But then you can also have unsymmetrical, where you have methyl ethyl or methyl T-butyl. Methyl T-butyl ether is actually an additive used in gasoline that they're trying to get out of gasoline because it's kind of environmentally persistent because the darn T-butyl group is too stable. So they're trying to change those things. So let's talk about how to name these things Well, let's start with the ethers. Ethers do not change the name. They are always a substituent. Just like the halogens, they're always substituents. They don't change the name. So what you have to do is look for the longest hydrocarbon and then add the substituent as a name. And how do we do that? Well, in this case here, we have one carbon and an oxygen. So one carbon's methane, but they have an oxygen there. So we want to count for that. So we call it methoxy. And that's our substituent, our methoxy group. If we have two carbons, ethoxy, right there. If we have the T-butyl group here, T-butoxy, T-butoxy, okay? And it's the substituent. And so you're gonna pick the shorter chain, turn that into a substituent and have your parent chain be the longer chain. So if we look at here, right in here, we have 1, 2, 3, 4, 5 carbons. So we have pentane, and ethers don't change the name, so it stays pentane, A-N-E. And then we locate where our substituent is, 1, 2, and we have 2-methoxypentane. Notice it all flows together. Common names have spaces. IUPAC names have dashes, commas, brackets, numbers, letters, and they all flow together, okay? So where's the longest parent chain in this one? Well, we have to do that and that right there because this is only one carbon, this is only one carbon, this is 2 carbons. So it's the longest chain. So our parent is ethane. And we have a methoxy on the 1 carbon and a methoxy on the 2 carbon. So we have 1,2 dimethoxy ethane. Okay, always a substituent. Okay, now there are a bunch of common ethers that are really used a lot. And so we're going to have to learn how to name those too. So for anything that is unsymmetrical, you're going to take the group on one side, the alkyl group that it is. So in this guy, it's 1, so it's a methyl group. Notice we don't have methoxy here because we're naming it. We're going to take care of that oxygen by putting the word ether at the end. So we have methyl and we have sec-butyl, and we alphabetize them. And remember, sec doesn't count toward alphabetization, but isopropyl does. If it's got a dash, it doesn't count for alphabetization. So the butyl comes first, space, methyl, space, ether. You know it's a common name because it has spaces, okay? But if it's symmetrical, you can just say diethylene because you have 2 ethyl groups with your ether. Your oxygen is taken care of with them. Okay. But now we have some weird ones, cyclic ones, okay? And when you have cyclic ethers here, what you're going to do is you're going to say what the cycloalkane would have been, but you say oxa to show you substituted one of those carbons with an oxygen. So that's why this is oxacyclopropane, okay? It's also called ethylene oxide, and another common name is oxirane. And we're also going to learn them as epoxides. So those are all the same name for the same thing. But oxapropane is the right word. And because the oxa is on the ring, it's going to be our number 1 position. The O is going to be our number 1 position. So when we have oxacyclobutane, we'll have a structure like this. Oxacyclopentane, or more commonly known as THF, tetrahydrofuran. Okay, why is it called that? Well, there's a molecule that is common in industrial, petroleum production that's called furan. It has 2 double bonds. And so what they do is they hydrogenate it, put 4 hydrogens on there, and take away the double bond. And we have tetrahydrofuran, tetrahydrogen furan. Okay, now it's one of our polar aprotic solvents, and it's a good solvent for a lot of reactions. So we want to make sure we know that that's THF. And then we have another one here called oxacyclohexane. It's dioxacyclohexane, meaning we have 2 oxygens in the ring. One's in the 1 position, one's in the 4 position. Now, this is slightly different than the dioxanes that are used to be pesticides. The dioxanes that used to be pesticides were benzodioxanes. So they were actually like this with benzene rings. And because those are really, really strong bonds, and those are really, really hard to break, they really, really are environmentally persistent. And so we don't use those anymore, but we're still trying to get rid of them. So, okay. So now let's talk about the most fun group of ethers, and that's the epoxies, okay? The epoxies are the most fun because they are the most reactive. Once you get up to tetrahydrofuran, we use it as a solvent because it doesn't react with acid, it doesn't react with base. It's very, very stable. But this ether is not as stable. It reacts very quickly. Why? Remember that cyclopropane had the most ring strain, right? Well, we have just as much ring strain in here. It's willing to pop open. In fact, all you have to do is hit it with a nucleophile on either one of these carbons, and it will spring open and generate an anion. So you can attack either side of this with a nucleophile, and it will spring open immediately, okay? So, you ever done 5-minute epoxy, right? Well, in 5-minute epoxy, you have these two little tubes squeezed together, you kind of push out. One of them is kind of a thick thing that's colorless. That's your epoxy. It has one or more, it usually has 2 to 3 different epoxy groups hooked together. And then the other side is actually a solution of a nucleophile. It's usually an amine. And it's nucleophilic enough at room temperature to make a cure at room temperature. So the amine portion, the stinky one, is the one that acts as the nucleophile and opens up the ring, generating a new carbon-nitrogen bond and an OH. And because there's multiple nitrogens in the stinky part and multiple epoxies in the other part, they make a whole network of bonds that can't be dissolved. And they're very strong and they're very durable. Okay. So that's why epoxies are so fun to use in those, but we can use it for other things too. We're going to use it for other things. Okay, so let's talk about our epoxide nomenclature. We actually have like technically 3 naming systems for these because they're used industrially so much. They come from what you've made them from. So in the case of ethylene, if you oxidize ethylene using the right chemical, we're going to end up with ethylene oxide, or also oxirane. Okay. But if you made it from propylene, you're throwing propylene oxide. You took your double bond, turned it in that 3-membered ring, and did it that. So that's one way to name things. Okay. And that's the common name. The common name is what alkene you made it from. So if you made it from butene, it would be butene oxide. So it's that simple. Okay, the first kind of systematic naming system is we're going to use the name oxirane. Okay, and when we use the name oxirane, you must start numbering from the oxygen. If you see oxirane, you must start numbering from the oxygen. So let's use that. I'm going to switch over to blue because that's the naming. Oops, that's not blue. No. Over to blue. So when we're having this, we have ethyl oxirane. So we're naming the ring. Remember when we had rings, if the attachment was longer than the ring was an attachment. If the ring had more carbons than the attachment, the ring was what we named it for. So we're naming it for the ring here because we have 2 carbons in one, and we have a total of 3 in our ring. Okay, so that means we have oxirane, and ethyl is the substituent. But why is it 2? Well, in this nomenclature, we go 1, 2, 3. So we have it on that system. Okay, and let's look at this next one here. We have 1, 2, 3. So that means we have a methyl group on the 2 and a methyl group on the 3. Okay, and if we go to this one right here, 1, 2, 3, we have 2 methyl groups on our 2. Okay, so that's one way to do that, and that's if you're going to name it for oxirane. Okay, if you're not going to name it for oxirane, you're actually going to have the word epoxy in there. We do it a little differently. Epoxy now becomes a substituent. Notice it's up front. Okay, that oxygen is the substituent. So what we do is we find the number of carbons in the parent chain, including the epoxy. And so in this numbering system, we're numbering the longest chain, which is this butane right here. And so it's going to be 1, 2, 3, 4. So in this case, it's 1, 2 epoxy butane. Okay, epoxy butane. So the oxygen is on the 1 and the 2 using the epoxy nomenclature. Okay. So that means on this other one here, we also have butane, but now we have 1, 2, 3, 4. So it's still 2, 3 epoxy butane. Okay. And when we number from this side, we could only get to, let's see, 1, 2, 3, and then this becomes a substituent. So that means we have 1, 2 epoxy, 2 methyl propane. That's the second systematic method. Okay. Make sure you know if it has oxirane, you start numbering at the oxygen. If you have epoxy, you're trying to get that epoxy on the lowest substituent possible, but the longest carbon chain possible. Okay, questions on that? Okay, all right, so let's get into some reactions. So obviously we've already made some reactions and we focused on the alcohols, but some of these reactions also can make ether. So I want to draw some attention to this. This is of course chapter 8. And so we're going to play with that a little bit. And in this case here, we did our hydration of an alkene right here. So water and a drop of sulfuric acid is good enough to make it, but the mechanism made it go through a carbocation, therefore you had a rearrangement. And that's how we made our tertiary alcohol from this substrate here. We made our carbocation and then it did a 1,2 methyl shift, and that's why it's on there. But if we remove water from our system and or instead replaced it with an alcohol, okay, water is a poor nucleophile. Alcohols are also poor nucleophiles. And so they will wait around for that carbocation to form, and they will also form a reaction at that carbocation, but now we have an ether. The difference between an alcohol and an ether is water or an alcohol. All alcohols will form ethers. All water will form alcohols in this catalyzed system, hydrolysis system. Now, if we go back to another reaction we have here, take away the carbocation, and then have the oxygen hit on the more substituted side. So it's still Markovnikov's, and so we can keep our secondary alcohol, but we can do that also with our alcohols too. Go away from water, react it instead of in water, react it in an alcohol, and you can make the ether. Same mechanism, nothing's different. We're just making ethers more now than we were a couple chapters ago. And then of course, the last one, we can't actually make the ether with the borohydration oxidation reaction because we're actually oxidizing the boron off with the oxidizer peroxide. And we don't have it. If we were to put a per alcohol in there, it would probably generate radicals and not work. So you typically don't make ethers from that method. Okay, but we still need a method for making a primary ether. We probably already done a reaction that does that, I think. All right. So that reaction was the SN2 reaction. We can also make primary alcohols if we have a primary alkyl halide and a good nucleophile. Okay, remember, once we got to secondary, it was starting to compete with E2, and once we got to tertiary, it was SN1 and E1. So we can only do this with primary alkyl halides. Okay, so in this case here, we take our hydroxide and use it as our nucleophile, do an SN2 reaction to give us our alcohol here. But if you instead make the salt of your alcohol, turn it into an alkoxide, so it's a nucleophile, instead of just a poor nucleophile, it's a good nucleophile because that has a negative charge. You can then displace that on primary carbons primary alkyl halides to give us a symmetrical or an unsymmetrical ether. What's the difference? Well, on this side, we have 3 carbons and we're attacking it with 1 carbon. So we're going to have an unsymmetrical ether. On this one, we have 2 carbons and we're attacking it with F oxide, which has 2 carbons. We made a symmetrical ether. Okay, so it really can be done with, you know, the wide variety of things you can do is important. Okay, now, this method has another name. It's called the Williamson ether synthesis. Okay, and so it's just a nice SN2 reaction, great way to make primary ethers right here. And there's several ways to prepare this. One of them is where you take metal, like sodium or potassium, and actually drop it into alcohol. Okay, and what it does is it does a electron transfer, turns it into sodium plus, and then you have to use 2 equivalents. It takes the hydrogens from the alcohol, turns them into hydrogen gas, and it bubbles out of the solution. And so it's an irreversible reaction. You have as much alkoxide in there as you had sodium or potassium. Okay, so that's really cool. The other thing you can use is any base more basic than alcohol. So we have to think about that is alcohol has a pK around 19. Hydroxide would be the conjugate base of that would be water. pK around 15. So it's hard to make an alkoxide using sodium hydroxide. You have to use something more basic. So when we do that, we like to use things like the cyanide ion or the amide or even the anion made on carbon to make a nucleophile. Okay, so that means most of the time we're looking at stuff like sodium, amide first. Now notice this is a 2-step reaction. You want all the sodium amide to react, because if we don't, it might act as a base. Okay, so or it might act as a nucleophile on our substrate here, our alkyl halide. It might act as a base. So we want to react all that first, form a whole bunch of your alkoxide, and then add in your alkyl halide, preferably primary, and get your ether synthesis from that. All right, so we already know the reaction. We even know the reagents, but now we can specifically call out whether or not we want alcohols or ethers by choosing our selection. All right. All right, I'm gonna finish with this one because I don't want to go too far ahead of the other class. And so there's actually a right way and a wrong way to do the Williamson ether synthesis. Okay, because what did I say was a requirement for the alkyl halide? It has to be primary, right? So it'll react. Remember, we have strong bases. Secondaries and tertiaries go by a different mechanism. They go by E2. They go by E2. So we can't use secondary or tertiaries. We can only use them for primaries. That means we have to build our molecule correctly. So in this case here, if we wanted to make this isopropyl methyl ether, we could do it a couple ways. We could do it, break it where it's here, and so we have a nice small alkoxide, but we have a secondary alkyl halide. We might end up using it as a base instead, right? Now, if we go over here and cut it here, that makes the methyl group our alkyl halide, our primary alkyl halide, and makes our alcohol the secondary alcohol, but it's still nucleophilic. Tertiary alcohols are not that nucleophilic, but if you only have a methyl halide, it only has one choice. It can only do SN2. Okay. So that means when we want to do this attack, you want to have the primary part of that alcohol be your alkyl, primary part of your ether be the alkyl halide, and the other half of the molecule be the alkoxide. All right, and yeah, I'm gonna stop there. Okay, thank you very much. We have class on Monday next week, and we will continue on this. We should finish up this chapter by Wednesday of next week, and we should then have 2 days to review for our exam and final. Okay. All right, any questions from home? Okay, I'm going to go ahead and stop sharing. I'm going to stop recording.